Hi everyone. My name is Richard Koss, and I'm with Pressure Vessels, and we're going to talk about static pressurized equipment tonight. And didn't quite mean to advance it yet, Amy, but that's okay. I'll be talking for most of the time. However, Hong Lim is going to be coming in a little bit later for a portion of it and speak. So go ahead and advance. I think to begin with, we'll talk maybe a little bit about organization before we get to the safety moment. But the pressure vessel department is part of the mechanical engineering, and as you can see, there's 6 groups within mechanical engineering, and pressure vessel happens to be the #1 group, as you can see there. It's at the top. So it has nothing to do with the fact that I made the list, but there it is anyway. Okay, going on to the safety moment. 1 square inch. All of you should have gotten a little square. Now it should be 1 square inch. Now I want you to think about that, because pressure is, in this country, we usually, as a unit of measure, we use pounds per square inch, or PSI, which is the same thing. And whenever we talk about pressure, people forget how much pressure that really is, because 15 PSI, what is that? Well, that's about 2 gallons of milk on an area that size. And that's fairly low pressure. When we talk about pressure from a process standpoint, 15 PSI is nothing. But yet, it's 2 gallons, at least, well, it's a little over 2 gallons of milk on an area that size. So, going back, just I'm going to tell you a little story about pressure. How many people, how much pressure is in your cars? In the tires of your cars, how much pressure is in it? About 32, 35. Now that's about 4 gallons of milk on an area, 1 square inch, but it's over the whole surface of the tire. Now that's a lot of energy. Now a few years ago, a friend of mine, his teenage son had gotten a job at a tire shop, and he had just gotten it, and one of the first things they asked him to do was they took a tire off a car, and they asked him to take the tire off the wheel. So he went over, put the tire on the machine. And you guys have all seen that machine. It's a big hydraulic machine that comes down, smashes the tire down. The only problem is nobody told him that he had to take the air out. Now that sounds funny, but unfortunately he was killed as a result of the explosion when he brought the machine down on the tire. And that just shows you that 32 PSI, the explosion. I'm sure the pressure went up higher before it broke, but unfortunately he was killed. And I just wanted to emphasize that pressure can be very dangerous. And I was going to show a blown up vessel, but I understood that a lot of people in previous classes had shown blown up vessels, so I thought that maybe I'd pick up something different. So we can go on to the next slide. Aerosol cans. This is something I found here where in Texas somebody had put an aerosol can in their car. It was sitting there. It was 100 degrees outside, so probably the car was 140 inside, especially in Texas. It gets really bad there. And I don't know, you can read through this. This was a deodorant spray can, and unfortunately it exploded. You can go on in, and this is the result. And you imagine if somebody had been sitting here while this deodorant spray can was a projectile going from probably the front of the car into the back seat, it would have done a lot of damage, and it would have. It might have even killed somebody if it had been, the right position or whatever, So it's just to keep in mind, aerosol cans in cars, not a good thing. So we have lessons learned. And don't leave the pressurized containers in your car. It's a good idea. And, take the manufacturer's safety recommendations. And, of course, especially things at work here, you want to report any incidents that might be unsafe practices in the workplace, or in your car for that matter. So, just be careful. Don't be putting, pressure can kill. There's a lot of potential for bad things to happen. So going on. All right. So this is our overview. We're going to say, we're going to talk about what is a pressure vessel. It has to be code pressure vessel. We're going to talk about the vessel engineering workflow, which is probably very similar to some of the other mechanical disciplines that have been in here already. We're going to talk about the flow of information among the disciplines, which is a little bit of which is kind of a follow-through of the previous area of the vessel workflow. We're going to talk about pressure vessel design. We're going to talk about the fabrication of pressure vessels and transportation and erection of pressure vessels. And then last but not least, we're going to talk about storage tanks and API 650, which is the most common code that we use in this industry for tanks, and a little bit about how tanks differ from pressure vessels specifically. And so these are the topics that we will be talking about. So you can go ahead, Amy. What's a pressure vessel? I happen to have a pressure vessel. Here's a little pressure vessel. And as you can see, it's actually stretched very close to its elastic limit. Now, we don't design steel pressure vessels to these kind of limitations, but we've gone way beyond elastic limit, and this is a pressure vessel. I'm not sure what the pressure is inside, but it is definitely higher than the pressure outside. So, and as I said, you always need to be careful about pressure vessels. Okay. Here's an example. You guys probably didn't think about it. Here's a Coke can, and it looks like this one actually exploded here. Got overpressurized somehow. And, it's another example of a pressure vessel. Pressure vessels are pretty much any kind of container that has any kind of pressure that's greater or less than the pressure outside. So, going on, and I think this is a classic example of a pressure vessel. Even in the refinery, this is what we have. We have a pressure vessel, we have a pressure regulator, we have some kind of vent, we have well, you don't necessarily have the handles, but we we have a lot of aspects to this is what you see in a refinery for a pressure vessel, because you don't want to overpressurize it, and you have to be careful with it. It's just like any other pressure vessel. You have to have the correct safety devices on it in order to keep it from blowing up in case you get an overpressurized situation. So you can go ahead. Now this is another example of a pressure vessel. This is mostly external pressure. And I don't know what submarines are designed to for depth, but I don't think it's real high or real deep into the ocean. But it's definitely a condition that where you have an extreme external pressure condition, which is way beyond what you see in normal things that we talk about, that we deal with in refineries. So you can go ahead, Amy. Here's another example. This you see on the road every day, and this particular truck has a pressurized gas trailer, and we don't. This isn't something that we normally design in our industry, but this is another example of a pressure vessel. So, here's another example of fiberglass reinforced pressure vessel. We do see these from time to time, and it doesn't happen a lot, but there are some extreme times, certain processes where we would have this kind of a pressure vessel, such as there's some acids that really don't work well with too many metals, and this would be a use for that particular type of process. And this is just an example of a very fairly large and heavy pressure vessel being installed. And again, just to show you a little bit about the variation in size, from something that's very small, the size of a balloon, or even less, to something quite large, that can be hundreds of feet in diameter and up to 30, 40 feet in diameter, even more. In spheres, in cases of spheres, I've seen them 60, 70, 80 feet in diameter. So you can have some very large diameters and very large vessels overall. And like I said, the energy that's in these this kind of a thing, depending on what the pressure is inside of it, can be a lot. Go ahead. This is just another example. Here's on the right is a sphere, and on the left is just a horizontal vessel. And it's a fairly small sphere. As you can see, it's only got about 6 or 8 legs on it, so it's probably in the 20 foot diameter range, and it's hard to say what this horizontal vessel is. But and here's Chekhov has to explain it to Captain Kirk, so we need to have the definition of what a pressure vessel is. So we have to make sure that we get the definition correct. So, okay. What's an ASME pressure vessel? Okay, an ASME pressure vessel is a pressure vessel that's built to strict design, fabrication requirements, testing, and inspection requirements. And all these inspections all these requirements are defined in the ASME boiler and pressure vessel code, and this is the main code that we use. Now, this right here. This is the way the code is set up. Now you have section 1 is power boilers, section 2 is materials, section 3 is nuclear plant components, section 4 is construction of heating boilers, 5 non-destructive examination, operation of heating boilers, care of power boilers, and section 8 is construction of unfired pressure vessels. This is the main area that we in the vessel group deal with, and primarily with Division 1 and secondarily with Division 2. And to be honest with you, I've never done Division 3. I've never had anything that was high enough pressure. We have Section 9, welding and brazing. Section 10, going back to the fiber reinforced plastic pressure vessels. And Section 11, inspection of nuclear power plants, and 12, construction of service transport tanks. Now going back to no, not quite that far. Going back to the Section 8. Section 8, all the components of the code relate to each other. So when you're in Section 8, it doesn't mean that you forget about materials here in Section 2. Because Section 8 refers to materials in Section 2, and that's true of Section 1. And Section 8 refers to welding and brazing requirements. So there's a lot of interrelationship and non-destructive examination. These are all related to Section 8. And Section 1, like I said, is the one that we use the most. But there are times when we opt for Division 2. So you can go ahead.
Richard?
Yes.
This is a good question, Section 8. When you say high pressure and very high pressure, is that a cutoff pressure for a range where you will be writing?
Yeah, there is. In fact, if we go on here, we'll talk about that a little bit. I'll get to that. Okay. Looking at Section 8, Division 1. Now, Section 8, Division 1, up until the year 1999, the safety factor was 4 to 1. Today, the safety factor is 3.5. And as I said, what that means is if you look at the material chart in section 2, it'll tell you that the ultimate strength for a material is, say, 70,000 psi. You take that, you divide that by 3.5, and you get 20,000. So for instance, if you take a carbon steel material like SA 51670, which is a very common carbon steel that we use in pressure vessels, that 70 stands for the ultimate strength. So that's the ultimate strength of that material. So that 70 at room temperature, when you divide it by 3.5, comes out to 20,000. Now, that's not true of every single material. But there are charts that identify the particular allowable stress for the use of any one particular material that are approved by the ASME code. So only the approved materials are defined in Section 2, and those are the only materials you can use that are acceptable by the code. So like I was saying, the code defines the size and pressure limits, defines the design, fabrication, materials, inspection, and testing requirements. So it gives you all those requirements, and it's required by law by the state of California. It's required by law by many other states, and it's required by law by some foreign countries. Now, that doesn't mean that they don't allow other codes, because there are other codes. We just don't use them in this country very much. There have been some instances where I have seen use of some other codes in this country, but generally that's not the case. But it just depends on the state, and it's really a state-regulated requirement. And every contract that we have, they do have to look into that, what the client wants and what the state requires. So you can go ahead. I put this in here. This is the introduction to the ASME Code Division 1. And it's called U1. And what it does is I just wanted to show you that nothing in the code is straightforward and easy. In U1, it defines and each one of you have this, but it's actually, I printed out full size. So if you go back a little bit farther, you'll find that you have a full size copy that's legible, because you can't see it on this little one. But what the code does is instead of telling you that these are the requirements for a code vessel, and these vessels fall within the purview of the code. And what it does is instead of doing that, it tells you what's not covered by the code. So if we go on to the next slide, with that first arrow, it tells you that we're not looking at the code. But the next slide is three main things. It tells you that it has to be greater than 15 psi. It should be greater than 6 inches in diameter, and it should not be over 3,000 psi. Now, that was your question. There's your limits for Division 1, is 3,000 psi. Now, that's relatively new, actually. That's probably the last couple years, because they used to build Division 1 vessels to much higher pressures, but they put that limitation in just a couple years ago, as a matter of fact. So, but I just wanted to put this in here to kind of show you that, there's a lot of other requirements besides those three requirements. There's some other limitations on size and pressure and process. And it's not really the most straightforward document, but it is there. So you could go on to the next slide. You can skip that one. And I just gave you the whole part of U1 so that you could read it. Now this is a logic diagram for the same thing. So what it tells you is, your first question is this vessel for human occupancy? Well, if yes, then it's not in the code. Okay? It's not something you want to see. So if it's a submarine, no. All right? So if it's yes, it's a submarine, no, it's not in the code. If it's not for human occupancy, then you go down here. Is the pressure greater than 15 psi? No. Then, again, it's exempt. So you kind of work your way through this thing. Yes, and I forgot what this is.
Flashpoint.
Yeah, okay, your flash point, okay, yes, and or no, and you work your way through here. Is it less than 300 psi? Yes, then you go on down. Indirect heated, you say no. So you see, it depends on which track you go, and you can kind of follow your way through this thing, and eventually you get to the point where, and as you can see, they didn't put in the 3,000 psi because this chart was actually done before they had that limitation. So that's something I probably should have added in there, but I didn't catch it until after I already had it in the slideshow. But now that doesn't mean that you can't build a vessel to ASME Division I requirements. You can build, even if it doesn't fall within this requirements. All it means is it doesn't need to be stamped by the code, or it can't be stamped by the code. But there's nothing wrong with saying, oh yeah, we would like to build it to ASME requirements because we want to have good quality. And many customers will say that, well, we want you to go ahead and build it to ASME. We don't really care that it's not really going to be at 15 psi, but we'd like to have something good that we can depend on, and they do that. But and sometimes they don't. But sometimes it's a good thing to get good quality, and it does guarantee good quality if you build it and inspect it to code requirements. You go ahead, Amy. All right. Right now, currently, fabricators that are allowed to use a code stamp in the United States right now, there's 2842 as of the end of last year. And worldwide, there's 2101 people who can build to the ASME code. They believe that in the next 10 years that this number down here is going to surpass the builders in the United States. So they're trying. I think that's part of what the ASME would like to do, is to become the premier international code, and I think that's one of the reasons why in 1999 they reduced the safety factor, was to become a little more competitive as a code with other codes in the world. So that's where we're at right now. So it's a growing use of this code. I think it's going to grow in the United States as well. But like I said, they feel that the code, people able to build to the code in the rest of the world will increase to a point where it will surpass the United States. Now this is an example of a vessel, and right up here that has a nameplate, and you see this little U with a little clover leaf. That's the stamp. Now that's what they pay their money for, and that's what they get qualified for, is for this little stamp here to identify that they're building, testing, inspecting, meeting all the requirements of the ASME code. This is just an example. just wanted to show you what that would look like. Okay, Division 2. We're going to talk about Division 2 a little bit. Division 2, usually, again, it's like any other of the code requirements. It is required by law in many states and foreign countries. Now, the safety factor in Division 2 is 3. And again, if you take the ultimate strength of your material divided by 3, that's your allowable stress value at room temperature. Now, Division 2 is in the middle of a big rewrite. And coming out next month, I believe there's going to be major changes. And one of the major changes is they're going to change the safety factor to 2.4. And with that, I would guess they're going to make changes to the requirements, to the testing, and just the general quality requirements. And that's really what the Division 2 does right now. The quality requirements are much higher than they are for, and documentation are much higher than they are for Division 1. Also, the limitation right now for Division 2 is once you've defined a process. For instance, if you go out and buy a vessel to Division 2 and you say it's going to be a catalytic reactor of some kind, you can't change that process. That's it. That vessel cannot be changed. It's very difficult to get the process changed because that's what it's been designed for, and that's what they hold. That's what the paperwork says, and that's what they hold it to. So they don't want to make any changes to it. Now, what they're going to do with the new edition of Division 2, I'm not really sure. I do know that, like I said, the safety factor is changing. Also, they're changing some of the X-ray requirements by the code. So I'm not sure exactly what's going to happen. I haven't seen any. I haven't actually seen any paperwork. I just got this information. So, okay, let's talk a little bit about the vessel engineering workflow. And where are we at here? Okay, this is the equipment that we normally would buy. Coarse pressure vessels. Your plain run-of-the-mill pressure vessels, horizontals, small verticals. Columns are, of course, your larger columns like this one here, fractionator columns, reactors, and smaller drums, horizontal and vertical drums. We also purchase the vessel internal, so that includes trays, mist eliminators, any kind of packing, supports for any kind of catalyst, all those kinds of, almost anything that's inside the vessel except for the catalyst itself. We purchase storage tanks. That's both shop fabricated and field fabricated. We purchase, and of course, spheres. And I think one of the things that gets kind of on the side, we do the purchasing and design for ladders and platforms such as what you see right here. So you can go ahead. Okay, well, this is kind of an overview of what we do. We provide the engineering design procurement services of equipment such as pressure vessels, etc. And including cryogenic vessels, and we do see that quite often in certain jobs that we've had. We do the mechanical design for internal trays, so we do check the structural capability of the trays, the packing and catalyst supports. So we do the design of the supports for catalysts. We do the design of ladders and platforms, pipe supports, pipe guides, And we check the lifting attachments and local shell stresses. And that really relates, the local shell stresses really relates to all these items that we're designing here. When you talk about internal trays, you can have local stresses. When you talk about packing and catalyst support, you can have local stresses inside the vessel. And then ladders and platforms. Now, for any structural people, have any structural people here? Okay, for structural guys, I know this is going to be hard to take, but we actually do design the structural steel for the ladders and platforms that are outside the vessel. Now, I know that's difficult to understand, but we do that because we have to know, we have to determine, not only do we have to determine the strength of the structural steel itself, but we have to know what kind of loads are on the vessel.